This is how surface area affects air resistance of an object. This is the final experiment project for the physics lab by Ricardo, Vasquez, Yosmanni, Reeves, and Drake Scott. So for roles, Yosmanni was data collection and recording, Ricardo was calculations and interpretations, and Drake was recording and interpretations. For our initial hypothesis, we thought the surface area of an object is directly related to the force of air resistance applied on that object during its descent. And for our method, we were going to measure the surface area of 3 different objects, a basketball, a baseball, and a book. And for consistency, one member, Yosmanni, will drop the 3 different objects from 3 different heights with 3 trials at each height, totaling up to 9 descents per object. And from this data, we'll have distance and change in time. We can obtain velocity, and with velocity and time, we can infer acceleration, and with acceleration, we can get the force of the object due to gravity in the physical world. And by calculating the actual force of the object due to gravity and subtracting it from what we get in our data collection, we can actually make a lot of inferences about the force due to air resistance acting in the upward direction, and we can also decide and see how it changes in objects with different surface areas. So pretty much 3 different objects from 3 different heights dropped 3 times each at each height. A basketball, a baseball, and a book. The heights are 4 feet, 6 feet, and 8 feet, and the meter conversions are there. So we're going to time their descent, get the velocity, and with the velocity and change in time, we can get average acceleration, and then we can infer the force due to gravity in the physical world. And by comparing this value to the theoretical value of the object's descent in a vacuum, we can understand how air resistance affects the speed at which the objects of different surface areas fall. So here are the properties of each object. To find surface area, the equation we used is next to the actual value for surface area. So for the basketball, mass is 739 grams, surface area is 8,107.32 centimeters squared. For the baseball, the mass is 145 grams, the surface area is 167.42 centimeters squared. And for the small book, the mass is 373 grams, and the surface area is 723.67 centimeters squared. So here's our data collection. Yosmanni dropped the objects at the different heights. The table below shows the 3 objects. The second row is the first trial at 1.22 meters. The third column is trial 2 at 1.83 meters, and the fourth column is trial 3 at 2.44 meters, and all these values are in seconds. So now for calculations, Ricardo used the kinematic equation x equals a times t squared, acceleration times time squared, all divided by 2, plus the initial velocity multiplied by time. And using this, we could find the average acceleration of each object, and you see it below. This is same as the last chart, except it's in meters per second squared for each object. So now for calculations, for the latter part of calculations, we use Newton's second law, which states that the sum of all forces is equal to the mass times the acceleration. So the force of gravity going down minus the force of drag going up is equal to the mass times the acceleration. Algebraically altering the equation, we get that the force of drag, or air resistance, is equal to the force of gravity minus mass times acceleration. And in the chart below, you can see in newtons the calculated force of drag for each object at each different trial. So in conclusion, as predicted, the surface area does seem to affect the force of drag on an object's descent. The basketball has the largest surface area, and it also has the largest upward force of drag in every case. This trend stays true for the other 2 objects as well. The baseball, having the smallest surface area, also has the smallest upward force of drag or air resistance. The small book had a surface area in between the other two objects, and that also corresponds to its upward drag, which was in between the other two objects' values for drag. This stays true for all three trials at each different height. So that's our experiment. In reflection, stuff we could have done better. Our data collection method was on a relatively small scale. The three objects and the three heights were relatively small and relatively low. So while we can make inferences about the physical properties of air resistance and surface area, how they interact, it's not really significant enough to make a very concrete assumption. Another issue we found was that we did use three objects. They were all relatively similar in size, all quite small and all not very massive, and they only encompassed two shapes. A rectangular prism, which was the book, and a sphere, which was the baseball and the basketball. Obviously, more varied objects would help us paint a more detailed picture. So perhaps use more objects of different sizes, different surface areas, different shapes in the future. And also to improve data collection, we decided that the use of lab equipment, such as motion sensors and perhaps like online technological graphing programs, could streamline and perfect data collection. It would help get a lot more objective data points for each trial. Furthermore, another way to improve the credibility of the experiment would be to have just more than one experimenter collecting data. Obviously, we'd get more data points, more objective data points, and it wouldn't rely on one person's possible human error. We could have a more varied approach and understanding of how surface area actually does affect air resistance. Finally, the most obvious method for a more elaborate and specific experiment in the future would be to utilize a larger number of heights and trials. This would add variety to our data and make it more concrete.